All right, I am going to go over the following concepts associated with floating point numbers, and let's start this off. First of all, you do realize the difference between double precision and single precision, correct? So let's just go through this again. Oh, look at everybody hovering over that thing. If this were single precision, what would it be? Did I spell that right? All right. So 1024. Why did I choose that number? It's really easy, right? So that should be 10000000000. Am I correct? Okay. Why did I choose that number right there? Well, it just so happens to be 1/4 plus 1/8 plus 1/16. So I chose this all because it was really easy, right? So, remember, with single precision and double precision, we normalize. So we always assume there's a 0, or I'm sorry, there's a 1 in the first place. So that means that we're going to move the decimal place over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places, right? Oh, this is not on. This would help immensely. There we go. You can hear me better. So we know that with single precision, we have, for the exponent, we have 8 bits for the exponent. So since we're moving it over and we're normalizing, we have 8 bits is from 0 to 255, correct? So we have 127 plus 10, 137, which is represented by the number 1000. Say that again? No, I'm doing single precision right now. All right? It's because I'm going to see single precision right now. All right? 1011. Is that correct? Yes? Yes? I'm just doing this from the top of my head. I'm not even using a calculator. So let me look at somebody else's. Oh, you know what? It's 1001. I showed 1011. That's a lot more. Okay, good. That's why I checked on this to make sure I did it right. Correct? The sign is positive. So for single precision, my sign is 0. My exponent is 1000, 1001. And then I'm going to have 1, 2, 3, 4. That would be, if I'm going to group these by 4. You guys remember, the camera's picking all this stuff up, so there's only so many, so much we can hear. 1 0 or 0 0 0 0 0 0 0 1 1 1 0 0. Let's see, we have a total of 23. Correct? Zero, 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 zero. Would you agree that that is single precision? Is that a yes or no? Yes. All right. So with double precision, which is what I asked, Does this number here change? It's the same thing, right? And so, at least when we're moving it over, it'll be the same. Oh, excuse me, I'm allergic to floating point. So, our exponent is how many bits? 11 bits. So that means our bias is going to be what? 1023. We're going to add 10 to that. 1033. So the exponent is going to be, hey, remarkably, 1, 0, 0, 0, 0. Let me get this all right. Well, I know my last is going to be 1, 0, 0, 1. So let's see, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Does that seem reasonable? Okay. And then, of course, the end is going to be the same. So we're going to have, again, 0, followed by 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1. Followed by 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 0, 0. A total of 52 bits, right? Agreed? Agreed. Okay. So the only thing I have to do is determine how many points you get for identifying all those. So we'll look at that later. All right. What is the obvious thing that's going to happen with this next problem? Oh, shoot. You all assumed, I hope you all assumed that that was lowercase a, right?
Nope. Knocked you off for that, man.
Oh, gosh. Oh, look at this thing. This thing auto-corrected everything. It auto-corrected everything. Because this was supposed to be lowercase c. This is what I get for not checking what stupid Microsoft Word does.
Sweet.
Yeah, I said you got errors for undefined variables.
That was not the thing that I was looking for. Yeah, I hate when this happens.
I said, will I recognize capital? What if they were to execute? You have to find because they have to
I'll tell you what, I won't count that one, since the intent was there, but it wasn't there. All right, so let's say that is lowercase a and lowercase c. Very good for those of you who recognize that that was a capital letter and C. It's not the same. But the intent is what happens. All right. It will create a division by zero exception. A division by zero exception means that what is going to run? Some ISR, right? Some interrupt service routine that has been identified in a zero exception. Which, by the way, if you don't write it, what happens? Well, you're not all that sure, are you? Right? That's why it's always good to set up, well, in most of these cases, I think in the table for ISRs like this, it automatically goes to just a return from exception. So in other words, nothing would happen. It would just come back from it. Which might be very bad, because if you divide by zero and something happens such that that's not what you expect or want, you should at least handle it gracefully. But something else happens. And this is what I wanted you to look in the book for, is the floating point status word is going to change. It's going to identify that there's something going on, like denormalized number is handled at 0, and the division by 0 flag has been set, and the floating point error summary flag has been set. And so later on, what you will need to identify is when you get into more robust embedded systems, is that you will need to actually, in your interrupt service routine, examine the floating point status word to identify what to do. Now, this would be a good question. What happens if you have a divide by 0? Now, obviously here, we force it by having a 0 there. But this could very well be a variable that eventually is equated to 0. What should happen? What should happen? Just toss out some ideas. What do you think? All right. One recommendation, A remains the same or C remains the same? Now, some ideas, right? So we could look at some ideas. And in fact, I think in the process of this, I don't think C is even going to change. I think immediately when it tries to do the operation and encounters a 0 or a divide by 0 error, it will not even change C, and it'll immediately go to the interrupt service routine. What else should you do in the interrupt service routine? Wow, nobody's offering an idea, or everybody's kind of zoned out from turning in the last assignment? Well, since I don't have very many people offering any suggestions, I would like to have you think about it, because you never know, it may show up on an exam. So maybe you should think about some concepts that don't necessarily have to give you the answer here. I need you to think about, in other words, this is a problem that you need to think about. What does it mean if you divide by 0 and you're doing computation? This is where I do the big, huge pregnant pause, and everybody looks down at their shoes or something, because they don't want me to call on them, because I'm about to call on someone. Can you recover? I mean, should your system totally shut down if you divide by 0? All right? So obviously you need to do something immediately to make sure that everything is stable. And in fact, in the next lecture, we're going to talk about the watchdog timer and how maybe the watchdog timer will indicate that there's a problem as well. But that's beside the point. Right now, it's a divide by 0. Yes?
This is the last lecture.
Kind of. We'll go on. This will become clear in about 5 minutes. All right? Notify something. All right? So here, let's write this down.
Can you just disregard and then continue?
You disregard. Do you save all pertinent info? Do you stop and die?
I like that one.
Do you notify someone? Now, imagine you are the Mars shuttle, not the Mars shuttle, the Mars spacecraft, which is now in descent from the Martian atmosphere, from an orbit above the Martian atmosphere, and it is parachuting down to the ground. All right? And you get a divide by 0 error.
Whoop. It's abandoned mission, guys.
All right? So, do you just stop
Yeah.
and then let whatever happens, happens? Right? Do you reboot?
Just figure out
Right.
what policy there.
Go back to the earth.
This is why in some situations you have critical systems that are redundant. So for example, in the space shuttle, in the early part of the space shuttle, there were 4 processors that ran simultaneously, and it was a voting system. If all 4 voted, or if all 4 did the computation, and 3 came up with one answer, and 1 came up with the other answer, they would take the one with 3. All right? If 2 came up with one answer, and 2 came up with the same answer but a different one, they would actually go to a 5th system. And the 5th system was manufactured by somebody else altogether, and that would take over. And the reason for that is because in space, you have what they call upsets. Is that the right word? I think that's the right word, upsets. In other words, a cosmic ray comes in and flips a bit. And suddenly you have a problem. And that's why you have redundancy like that. So in this case, I might come up with a question saying you are this application and you come across a divide by 0 error, what do you do? So I'd like you to take a look at that. All right? So, with respect to floating point, we've already covered quite a bit of floating point concepts in earlier lectures. The main thing I want you to understand, of course, is the use of floating point, single precision, understanding double precision. By the way, let's take a look at this single precision versus double precision. What do you notice for this number when you represent it in single and double? Is there any loss in precision going from double to single? Not really, it's the same number, right? You're not dropping any bits. Now, can you think of a number out there that might be better represented as double precision versus single precision? Which one was that? Pi. All right? Pi is an extremely rational number, right? And the more, it's irrational, sorry. It's an extremely irrational number, right? And just as an approximation, in single precision, it may be good enough, depending on what you're doing, all right? However, let's think about this. If you are traveling on a vehicle, or with a vehicle, And part of your computation of traveling with that vehicle is determining, in fact, I'll write this down as I talk. So here it is an example. You're using single precision. And you are computing the distance a vehicle travels using some calculation associated with, you know what your diameter is, right? And pi, the number of revolutions, right? So will it depend on accuracy if you travel, let's say, 10,000 revolutions, right? What is your accuracy of the distance? Travel. So, one thing that you might have to do is you might have to identify what is the floating point representation of pi in single and double precision. By the way, how did we identify that? Pardon me?
Converting to binary.
I can't hear you.
Converting to binary.
All right? But how are you going to do that? What's the easiest way to convert that to binary? That's a lot of math, isn't it? Perhaps you compile it and put it in a variable in a computer and then just read what it records it as in the memory, right?
Well, I think you'd want to cut it off after a certain length because pi goes into like the hundreds of thousands.
But remember, this is single precision, right? So you're going to be limited by how many bits in floating point. Your exponent is, for all intents and purposes, a waste, right? 3 point whatever. So it's always, in fact, what is the exponent going to be? We already know what that is.
24 bits.
No, the exponent itself.
Zero.
So we know for a fact that pi is 3.14159, which right off the bat we know is going to be 11, this is in binary, 0.001 something. So we know that our exponent in single precision is what? 1000000. Agreed? Yes? And in double, it is going to be. By the way, the guy's talking back there. The camera picks it up because you're right next to the camera, all right? And I know that my mantissa starts as 1001, and then it goes on to something, right? So, my question is, at what point does it matter if you have single precision or double precision? And this should be inherently obvious as you start looking at how many bits are in the mantissa. And this is anything having to do with double precision and single precision. If my number of revolutions is 1, will it make that much of a difference? My revolutions are 1,000. Does it make that much of a difference? Let's get closer. If my revolutions are 100,000 or 1,000,000, does that start making a difference? Yeah. So it comes down to when you are representing or when you are multiplying very large numbers, you start losing the precision at the end, and that's why you may want it longer. Now, in the end, if you're 1,000,000 revolutions, do you really care about 1 inch in the end? Probably not. So when you're looking at single versus double precision, there's going to be the trade-offs. Number 1, do you need the precision? Can you think of a situation where you might need the precision? Will I ask this on the test? You never know.
When you're counting the weight of molecules or something.
All right? When you're counting the weight of molecules, or when you're working with a lot of very small or a lot of very large numbers, when you're adding 2 very small numbers or 2 very large numbers, the difference between numbers will make a big difference, and that's why it's nice to have the double precision so that you can be as accurate as possible. But in a situation of temperature, right? Can you tell a difference between 72.155555555 degrees or 72.1555555 degrees? Yeah, I like that. So no, it all depends on the application. The other is, can you afford the time and space needed? And so from that respect, this is maybe something you should ask about. Do you use floating point versus integer numbers anyhow? So what if you actually identify the temperature and you only need tenths, right? So in temperatures, maybe you're going to have something XX point X degrees. C. You know you are limited by the temperature. This is for a room temperature application. You know that your room temperature application is going to be somewhere between negative 40.0 to positive, oh heck, even 50 degrees Celsius is a big range, right? So, do you really need to represent this as a float? Or can you do all the computation saying that it is negative 400 to positive 500 and just use an integer? Because an integer will hold that number, correct? 16 bits. Versus, how many for a float? 32 bits? 16 bits? And depending on your processor, sometimes these two operations, doing addition multiplication, takes a lot more time in a float than an integer. It just so happens that we have a floating point unit in our processor, but smaller processors do not. All right, any other questions on floating point? That is it for floating point. Thank you very much.